So I usually start most of my presentations with the idea that I'm a recovering oil and gas geologist. I've been 10 years renewable and I'm okay. We start that way because, one, I live in Calgary, so we take a bit of a beating in terms of working in the renewable energy sector. I got into this when it was $108 a barrel. That is not a sane decision to leave an industry that's that lucrative, but what I saw was a change, a significant change that was playing out in real time in the energy industry. And I wanted to be part of what I refer to as the next generation of energy. What we're looking at is a fundamental change in our energy economy. And it's happening faster than people realize or want to adapt to. I think a great example would be, how many people have a cell phone? Come on, you're lying, all you have a cell phone. You can just lift up your hands, not hard. Yes, I have a cell phone. How many of you had one 2 years ago? 5? 15. Okay, so 15 years, you've fundamentally changed how much technology you have in your pocket, right? This is the type of energy change that we're seeing right now, whether it's wind or solar or storage or distributed energy generation. So it got me thinking about, and I did a presentation here in Waterloo that was put on to talk about future energy resources. And at the time, it really got me thinking about what happens. This slide is actually almost a decade old. And it got me thinking of who decides our energy strategy going forward. Who gets to make that pick? Is it the people who are 60 and retired and worried about how their pension fund's going to go? Or is it the 22-year-old who's just graduating out of a geology department? Who gets to make that pick? Usually it's the 60-year-old guy who has the pension fund and the funding. He's making that decision, or she is making that decision every day with their dollars. So when we talk about investment into the next generation, it's not just about capital, it's about energy, time, resources, policy, it's all of these things. And what happened and what I saw, it was a little bit scary, is that we were looking at, if I'm looking 30 years out from an energy perspective, what is the energy economy or the economy as a whole going to look like in 2050? Does anyone have any idea what that's going to look like in 2050? Anyone putting financial bets on the energy industry in 20 years from now? Right? How good are we at predicting this? So if we go back, how many would predict the price of oil tomorrow, next week, or a year from now? Right? We're going to say it's close to $50. 2 years from now, anyone? Suggestions? $100? So the joke that I had when I was in an oil field operation and the price was close to $100 a barrel was nobody predicted $38 oil. There was a few people and they were considered crazies. But then a year later, we're looking at that price dropping, and it made me realize that I actually kind of want to pass on a really boring energy resource to my children. So the idea that my energy investment could be boring and stable and predictable, that's what really drove me into this industry. So I started looking at what do people invest in. The word geothermal is not in this slide. Shouldn't be anyway. Nope. Is it reliable? Is it a source of energy? Both electricity and heat. We forget about heat when we talk about energy. Can it supply me with something consistent? So Super Bowl Sunday, I want to turn, Grey Cup Sunday, I want to turn the lights on, do they go on? That is a normal, predictable behavior in Canada. If I'm in India in a remote community, I go to switch the lights on. That might be not the day that I get power. So when people have energy insecurity, they have a much better understanding of what transmission and infrastructure and everything else looks like. So this reliable source of heat is something that Canadians take for granted, which is one of the reasons we have energy literacy at an all-time low, because you actually don't know where your power comes from. What you then go is long-term revenues with known fuel costs. So I don't have a fuel cost in geothermal. Once I drill it, it's there. It's permanent. It's the planet of 4.5 billion years worth of heat. So what I'm looking for is the stability of a long-term revenue. Power purchase agreements that are 25, 30. There was one signed in BC a few years ago for 65 years. Yeah, that's a pretty good return. You're signing up for that, right? What we then want to look at is this a new and an innovative technology? Is this the fusion guy, right? No, these have been running for 100 and something years, right? So we have reservoirs in Italy that have been running for 110 years. We have literal power plants that have been running for 40 or 50 years. So this low centralized energy source that we all got used to, that you build a huge coal plant, you run it, it doesn't have a known revenue source because we may not have the longevity with the fuel costs. We might not know what coal costs us in 20 years with carbon tax or exploration fees or remediation. So this is one of the things that I loved about it. But the one that gets me and got me over and over again is when I started looking and realized I need a cheap power supply. Right? What do we classify as low levelized cost? Is it how much it cost in year 1, 2, or over the course of the project? And my work in remediation and reclamation in the oil and gas industry actually was one of the things that triggered me to the idea of it's not what it costs to build, it's not what it costs to run, it's not what it costs to clean up or fix at the end, it's all of it. So we have to incorporate that entire cost into our economic models. And I don't think we do that here in Canada very well. Those externalities associated with healthcare, fresh water, remediation, reclamation, all need to be incorporated into the cost of energy. So the last part was, if I'm going to build something, I want to make sure that the local community doesn't hate me for it. Just that's more of a personal thing, but in terms of investment, I don't want an environment where I can't actually build what I'd hope to build because I do not have the community, political, or First Nation support to do so. So this is why I think of it as the next generation of energy. It is the lowest levelized cost for places that have a geothermal resource. So if you're sitting next to a volcano, next to a power line, this should be your first option. And in many places around the world, it is. So California, New Zealand, Indonesia, Philippines, these all have an amazing geothermal resource, and they've chosen to develop it. I've even heard of this little country called Iceland, that apparently if you're on a diverging plate boundary and you don't have any other resources, you develop it first. Do you know what Iceland gets for bragging rights? Some of the cheapest power supply on the planet. Between hydro and the geothermal, we have people who are shipping, aluminum? Halfway around the world to be smeltered, and then halfway around the world again to be sold. This is what cheap energy can do for industry. The capacity factor is off the charts, so for any of you in the electrical side, utilities love places that can develop a 90% power supply. It is much easier to manage a grid system. And then the last one, and this was one that kind of took me by surprise, was the environmental footprint. I'm insignificant. Most of my infrastructure is actually buried. I put this slide up because people go, yeah, that's great, Craig, where are you citing your sources? This is the geothermal levelized cost of electricity globally. From a very sketchy source, this is the US Department of Energy. Looking at global data over the last 50 to 70 years, this is predicting going forward. Again, if you have a geothermal resource in your area, you should develop it first. The interesting part about this little black box is to say, what would I compare it against? So in my case, if I have geothermal, I should always do geothermal. The vision on this is that develop what you are good at and what you have available to you. So this is what we tried to shoot for. We have two projects as Borealis. One is in Terrace, BC. It's actually home to Canada's hottest hot spring at the time. It is a beautiful location in the mountains. It's actually about 160 kilometers south of a lava field. Obviously not a bad place to start looking for geothermal development. But we also have a really cool partnership with the Kitsillas First Nation. So this means that we're not just developing with First Nation support, we're literally developing a project with a First Nations partner. I love this model because they are excited about the long-term longevity of a project that covers that 7 generations idea. So they're going to develop an energy resource they can pass on to their grandchildren's grandchildren, as one of them quoted to me. The other project, which is sort of our pilot project right now, moving forward quite quickly, is in Valemount, British Columbia. This is an absolutely gorgeous scene. There's 2 unique properties about both these, is that we are looking at this from a very economic model. So these are absolutely phenomenal geologic opportunities, but the reason we're interested in them is because they provide baseload power delivery to BC Hydro where they need it. So I'm not putting it into the main grid system. I'm actually at end of line on both of these projects. That creates an opportunity for me to get to market with both my heat and my power. So a volcano that's in the middle of nowhere, I'm using the volcano example, or a giant fracture structure, has little value because I cannot sell my energy. This is welcome to pipeline world. If I can't sell my energy, how good is my project? Every one of the developers here has taken this approach because you cannot develop a project if you can't sell the energy. I repeat that because all of the science in the world is not going to make bad economics a successful project. There, that's the industry quote. That's the one you needed, right? Okay, perfect. This one's my personal favorite, though. This is a 300-kilometer power line that they have had on the books to fix for this poor community in Valemount for about 30 years. What they find is that it's really expensive to upgrade 300 kilometers of power lines, so Valemount ends up with the worst grid stability in the entire province of British Columbia. We can fix that. We can offer them a base load solution. And I think that that's part of the dialogue. They also have no natural gas infrastructure. So the electrical pricing and everything else involved means that they're in a position where they're using wood, electricity, and propane, shipped propane. So I'm loving that economic model and comparing it to a geothermal resource right in town. The other cool part about this, any skiers in the audience? I'm in Ontario. There's one. He's from Calgary. Yeah, this is going, Valemount Glacial Destinations is going in at almost the same time as we are in this area. It is going to have Canada's largest vertical drop. That means nothing to the non-skiers, but everyone else is probably excited. We've been doing everything from third-party validation, had other folks look at our reservoirs, people who work with the World Bank. It's great that Craig thinks it's a great reservoir, but it's always good to have third-party verification on all of that. We've done extensive, what we call an optimized geothermal exploration program, looking at all different sort of methodologies for de-risking the reservoir. And that's been a phenomenal opportunity to gather a ton of data points, but also using more and more of the mathematical modeling that you see in mining and oil and gas to develop better 3D models so that my drilling risk is lowered for my investor. That was the fundamental concern that we heard was early stage project for geothermal energy development is risky. How do I reduce that risk? One of them is drilling, the other one is finance. So, end of the day, we are hoping, I'm hoping to be top 3 for project developers in Canada. Is that better? I usually say first and then these two get grumpy, but the goal for us is to do this as an industry, is to build an industry that's developing geothermal projects across the country. And this allows everybody to grow. It's clean, it's renewable, we want them to have community support, we want the people that are involved with these projects to be successful so that we can build hundreds of these across the country. Thank you.
Thank you, Maurice, and thank you also to Armagan and Iris and Jessica for putting this symposium on. For industry, this is always a great opportunity to meet and collaborate with more the academic side of this industry, and to make some new contacts and see some old friends as well, so thank you. I'm going to talk about geothermal in a minute. First, I want to talk about Saskatchewan. So this project is located on the southern part of Saskatchewan, right along the US border. It's a pretty unique place to be. That's actually my hometown is Estevan, Saskatchewan. This project is just a little bit to the west of that by about 20 kilometers. Saskatchewan is a resource province. It used to be known as the gap between Manitoba and Alberta that everyone just tried to get through real quick. But that's actually changed. Saskatchewan's economy is booming. It's one of the strongest in Canada. We have a AAA rated government. It's, our investing in Saskatchewan is the place to be. We're the world's largest producer of potash, major leader in uranium development, and of course our oil and gas. Ironically, it's this oil and gas industry, a fossil fuel industry, that discovered our geothermal potential and our resources. This is a photograph near Estevan, Saskatchewan. This is horizontal drilling that's drilled into the Bakken Formation. We have almost 40,000 oil wells in southeast Saskatchewan. That's amazing. This becomes the geothermal database for what we're developing. I find it pretty ironic that a fossil fuel industry discovered and published all of this information. The regulations in Saskatchewan, I believe so in Alberta, is that the data from every oil well you drill must become public within 2 years. The potash industry is also moving a lot of fluids through solution mining in the Williston Basin. They have a holiday, or they get to keep their secrets for about 20 years, but the oil and gas industry has to publish that in a year and a half. So this is how we got to this project. We didn't go looking for geothermal. The oil and gas industry gave it to us. The aquifer that we're developing is a hot sedimentary aquifer. It's at the very base of the Williston Basin. The Williston Basin is a sedimentary basin, holds our potash, holds our oil and gas. So think go way, way, way down to the very bottom of the basin before you hit the Precambrian crystalline rocks. There's a 150-meter thick aquifer that spans all the way through Saskatchewan and into South Dakota. The geology is really boring, and in fact, we can trace the same geological units within this all the way into South Dakota. So it's a big, deep, boring, hot, wet pancake is really what it is. This is an idea of the well control in the area. This actually is a map that Craig made for us. Craig sat, all those little dots, those are individual wells, okay? Each one of those squares, I don't know if you can see the squares, is 6 by 6 miles. So this is hundreds of kilometers of well control. Not obviously all the wells went as deep as we need to go into the Deadwood Formation where we're developing, but it certainly, even the shallower ones, help develop this geothermal projected gradient. Some of those wells, Craig drilled. What did you say? You told me a story. You were in Lampman, Saskatchewan, which is a small town right in the middle of this cluster, and Stoughton, and I think you said you were standing on the roof of a bar, and you counted how many drilling rigs? I mean, there's a question coming after this. But it was like something that you could see 20 drilling rigs?
38.
38 drilling rigs. Visually could see during the boom years.
Little lights in the freezing cold.
Isn't that amazing? I don't know what you're doing on the roof of the bar, Craig.
That's another question.
So that's the resource side of this project. The other side of this project is that in Saskatchewan, we need power. So we need any power. Now, we need baseload power. We just simply need power. It's a small province of 1 million people, but we have a lot of industry, and that industry is booming. Our economy is booming. New potash mines are being developed, and we need power to supply that growth. In the past 5 years, we've seen a 16% increase in our power demand. We also have a very aging infrastructure. So think of all of that grid network across this province, which is twice the size of Germany. We need to upgrade that as well. This all comes at a cost. But secondly, on top of the fact that we just simply need power, we need green power. We need renewable power. Our province is committed to having 50% renewables by the year 2030, which makes projects, any renewable project in Saskatchewan, very attractive. These are SAS Power's numbers. Their projected growth for the year 2030 is that our current grid of 3,400 megawatts of power is going to increase to 7,000 megawatts. If we're going to have 50% renewables by that same year, we need to find 2,400 megawatts of power. This is a problem. This is a big problem that I hope that our geothermal project can be part of the solution. SAS Power takes this project very seriously for a number of reasons, all the reasons why we're developing this project. Number one, it's baseload power, it's green power, it's right located in the middle of their grid. In fact, it's located right in the shadow of 3 coal-fired power plants. Literally, you can see the coal-fired power plants from this project site. This is how they categorize geothermal for our project. This is going to make Craig twitch because they look at the cost of geothermal as being high. But what Craig pointed out earlier is that you can't just look at the capital costs of a project, you must look at the levelized cost of the project over the long run. And so although the upfront capital costs for geothermal tend to be higher than wind or solar, when you levelize the operating, the maintenance costs, everything like all of those factors, geothermal far outcompetes everyone. In fact, as Craig mentioned, it can outcompete natural gas. We've partnered with SAS Power in the past. In fact, they contributed $1 million to our $2 million pre-feasibility study. They want this project to go ahead. We've been meeting with lenders and financial institutions, and the message that we received was, well, if you don't have a customer, there's no way we're ever going to fund your project. And so we went to SAS Power and said, we'd like to negotiate a contract. It was, believe it or not, it was actually quite easy to do that. because of their need, right? If you go into a province that doesn't need power, that's a much more slippery slope. So we were able to announce in May of this year that we have Canada's first geothermal power purchase agreement. It's for an initial 5 megawatts. We have in reserve a letter of intent for another 20. There's no magic on that number. They just don't want to put a bunch of contracts on their books because of the liability. So that gives us a 25-year contract to offtake our power, 100% sales to SAS Power. It's a take and pay contract. Thank you. I glossed over this already. I think I'll skip ahead, but again, our project is going to be geologically boring. It is an aquifer. You know, this is never going to be a project where we're going to see steam rocketing out of the ground and you know, directly driving a turbine. This is 120 degrees, possibly 130 degrees, but you know, it's vast. And so the idea is that you know, the geological duplication of this will be relatively easy. From the work that we completed in the pre-feasibility study, to obtain the 5 megawatts net, we'll have to construct a 10 megawatt gross facility. We'll accomplish that through the drilling of 3 production wells and 2 injection wells. The plan is then to harness, obviously, organic Rankine cycle technology because we don't have steam. We have lots and lots of hot water. The hot water comes out of the ground. We harvest the heat through heat exchangers. That heat is then introduced to a working fluid, a refrigerant that can flash at low temperatures. That flash is what drives the turbine. We cool that refrigerant back down to the liquid phase for reuse. It's called binary, so you've got a loop of water and you've got a loop of refrigerant, but the two actually don't meet. They're separated by that heat exchanger. We actually have 4 of these facilities in Saskatchewan already, but not on geothermal. This, along the Alliance pipeline, so the big natural gas pipeline that goes through the province, they have these huge engines that are driving that product down the line. And so Alliance Pipeline has strapped 4 5-megawatt facilities at those compression stations to convert the heat from the engines and to produce power. So SAS Power is actually already buying this power, so they're very comfortable with this reliability. As Craig mentioned, you know, we're talking about a 95% capacity factor. This is as baseload as it's going to get. It's more baseload than hydro. You know, multiple plants then lend themselves to scheduled maintenance and shutdowns where you can work in unison with you know, a still small amount of employees. So the other thing that we discovered along the way, okay, I'm a geologist, I'm not a power engineer. We got really excited about, you know, geothermal and what this can do, and then, oh, we've got to plug in somewhere. I don't know. How does that work? So we had originally a project at one location not far from this site, so a little bit to the north, and we discovered that the substation that we wanted to plug into, that's my technical term, it was already saturated. There was actually no room within that substation for our project, and so we talked to SAS Power, and SAS Power said, listen, we need you guys, you independent power producers, we need you to get on stream, so we're going to build you a substation. So they built this substation right in the heart of our project area. It'll take 125 megawatts of power. It's been built as a plan for geothermal, solar, potentially some wind, and potentially a really neat flare gas project. We also have the subsurface rights underneath this location. So we're excited about this first 5-megawatt demonstration project. We were talking about demonstration projects this morning. I think it's really key that we get, you know, these initial projects, all of these projects going. How that matters for us as industry is that we can get the investment, we can get the banks to support these projects once a few of these are on board. We talk about the United States being the largest producer of geothermal in the world, and yet we don't have anything to show investors or banks here in Canada. Really important that we have actually a tangible unit selling power that people can visit. It's really important to get these first projects launched. For us, you know, once we have this first project on its way, the goal is then to develop multiple projects. Deep really aims to be a small to medium-sized independent power producer. Would love to get you know, a couple of 100 megawatts of power on track, but of course we need to walk before we run. We're personally invested in this project through our shareholder base and my partners out of Regina, who are investing $8 million. There's a total of $12.5 million of private investment that's gone into this project. There's $10.5 million of private investment, plus the support of $2 million from Natural Resources Canada and SAS Power. We're currently underway with an $8 million budget. It will be our bankable feasibility study. It involves the drilling of 2 initial wells. Really key to get that doublet in place, because once we have that data and refine our geological model assumptions, then we can get the construction debt to actually build this project. Without that initial wells, it just doesn't happen. I think we've heard this over and over again. People view drilling risk as too risky to invest in. Investors want to come in afterwards. It's getting the finance and the support and the funding to get the initial drilling is really key in getting over these obstacles. It's the inflection point. It's all this uphill with not a lot of financial support. Once you get to that inflection point, then ideally it's downhill from there. The blue sky in this project, our business case is power sales to SAS Power. But as we've talked about, there's the heat that's coming out of our plant, so let's say it goes in at 120, the water goes in at 120 degrees Celsius, it comes out at 65. We can't make any more power from the water after 65 degrees Celsius. So is there opportunity to sell waste heat from our geothermal facility to another industry? And so we're working here with Maurice and the University of Waterloo to explore those options. You think of greenhouses, and I actually have a friend who's just built this massive greenhouse in Saskatchewan. All of that was sourced from Holland. It came from these are Dutch. All the people, all the equipment, everything came from Holland for this massive structure. It makes me wonder, this really can't be that complicated. Why can't we do this in Canada? Why can't we design, build, construct greenhouses specifically built for the Canadian climate, specifically designed with the right LED lighting and the right support for Canadian products? I think the cross-Canada export collaboration opportunity on this is huge. So, thank you.
I'd like to thank Maurice, yourself, for putting this together, as well as you there, Armagon, and Iris and Jessica for facilitating the tables and just the whole, project together. That was very well done. Thank you very much. Clap, clap, clap. My name is T.M. Gunderson. I've now turned more into the COO of Epoch Energy, as my strengths are more on a technical side than they are on a financial side. But that being said, I'm one of the partners in this organization that's been around for about 1.5 years. I always love following geologists because they have very pretty pictures of downhole stuff, and this is going to be the prettiest picture in my slide. This is an area within Hinton there on one of the projects that we are doing. So one thing that Alberta doesn't, and I'm going to talk about the municipal geothermal opportunities, and this is going to be more Alberta-based. We are doing some work in the Yukon, but this is more of a heat opportunity. These two presenters talked about the power. It seems like heat is also the forgotten byproduct of geothermal. And when we're looking at Alberta, Alberta doesn't have the strongest power market right now. In Ontario, we're looking at between 150 per megawatt, 185 per megawatt peak hours. In Alberta, we're still talking $20 and $30. So we're talking 2 cents a kilowatt. One of the reasons for that is that there is quite a bit of coal production that's produced at about $5 a megawatt. Transitioning to natural gas and some other renewables, natural gas is looking at around between $40 and $45 a megawatt. So geothermal, even with your levelized cost analysis, it's still looking at $80 a megawatt hour. It could go down significantly, but it still does not reach the level for power production in Alberta. But what Alberta does have that a lot of other provinces don't have is 585,000 wells that have been drilled. That's a huge data set. We have wells that go down from 1 kilometer down to 5 kilometers, down to 6.5 kilometers. Bottom hole temperatures ranging between 60 degrees Celsius to 170 degrees Celsius. And so those are the opportunities that I'm going to, so it's not that there isn't a market for power in Alberta, it's just not economically there. Technically it's there, economically it isn't. And as Craig mentioned, we do need to be, we're developers, so we do need to have an economic reason for this to happen. So what I'm going to talk about, who we are, who Epoch is, the opportunities that we see with local government issues, solving those issues, new government mandates and favorable geology, and then what our plan is in order to capture that, and then go back to what we've done, and the final is the ask of what we need. So who are we? So we are Epoch Energy is a heat and power company, and we do deal with renewable, carbonless geothermal energy. We work with communities, which is our mainstay. So a lot of municipality. We have done work with direct industry. We're looking at implementing agriculture and silviculture into our projects, and some electrical distribution stability. Where it would work is in Alberta, is in isolated communities. Things that are connected to the grid, we're not really looking at right now as an opportunity. Well life extension, so what we're looking at is, of the 585,000 wells, we have high graded those wells for casing size, whether they're 60 degrees Celsius, 90 degrees Celsius, or 120 degrees Celsius and above. And then we look at how are we going to design a system using those well bores. So instead of, so it's the reverse of a lot of projects where we have a system, we have a need, we're going to design a well for that. Well, we have the wells, so now we have to design the system to be able to use those wells. Energy recovery from our existing oil and gas wells. Hinton has around 600 wells within a 10-kilometer radius, and that for us is an excellent database in order to get these wells, but they do have to be studied further. Thermal co-production with oil and gas. We are working with some hydrocarbon partners to potentially, they bring the oil to surface at 90 degrees Celsius, and we combine that with recovering the heat off the compressor station, and we can get that up to that 120 mark in order for us to make power, so that they can use it strictly right on site. Midstreaming assets, so this is our district energy system, and we look at building these district energy systems. I think Ontario itself has 20 of them. We're just going to look at supplying geothermal heat into these assets. We've reviewed about 20 different greenhouse vendors and manufacturers around the world, and we've got it up high graded to about 3 of them, and that's one of the uses for our heat. And then our industrial products, and we have a great grassroots movement in all our communities for job creation. And so the opportunity here. Well, as I just mentioned, there is job creation. So we're looking at putting a lot of our people back to work. We have an amazing talent pool of highly trained labor force to go from the oil and gas industry right into the geothermal. Food security, we really look at the food security portion of it because this is something that is very dear to a lot of people's hearts. I just came back from Yukon, I guess, a couple months ago, and one of the things that every municipality has is they want to not just food security, but they want to have food sovereignty. They want to be able to pick the food that they're going to grow. When we went up to Yukon, it was very real in that they do not have food sovereignty. They do not have food security. If their food trucks stop for a few days, the town runs out of fresh food. They are very reliant on a supply chain controlled by others for their very basic needs, which is not a situation any municipality really wants to be in. We have energy security. So when we say energy, we say heat and power. Canadian municipal energy leadership. There's a lot of funding and a lot of municipal organizations that are working together in order to get items like energy security and food security in there. and the future economic development potential, I would probably say that most, if not all, communities do have a 20-year plan for a greater sustainability, greater clean energy sustainability model. So going on to some of the local issues in the communities that we're working with, no natural gas or clean alternative backup energy source. And they have high economic expense for carbon fuel sources like diesel and fuel oil. Food security, as I just mentioned, they're importers of food. Most of our food comes from outside, even outside this continent. Like we're the top two energy and food security are two main topics that are talking about at NAFTA. And then when we were looking at some food production, we were talking with one food distributor that showed me a picture of a truck full of tomatoes going through snow, and it was in Mexico. And all the text said was, tomato prices are going up. That's something that's outside of our control, and that we want to be able to control it. Environmental concerns, we do have heating oil storage. There's widespread leakage issues. Some of these contaminations are sitting over top of the municipal aquifers. And then the well site cleanups after decades of operation. One of the big elephants in the room in Alberta is the imminent carbon tax, and that's going to affect the supply of everything. With supply of natural gas, diesel, and fuel oil are going to bear the carbon tax. Consumption of fuels will bear carbon tax. Per gigajoule of natural gas is going to be $2.50 with a 50-cent carbon tax on a commodity in Alberta that was traded at 68 cents back in May. And all our imported food will bear the cost of carbon tax. That's going to be the logistics and burning the fuel for transport. So the new government mandates federal Liberals and our provincial NDP, you can also say this for pretty much every province, economically driven, diverse community, green, sustainable future with a plan to action leveraging entrepreneurial opportunities, working with First Nations, and expanding the mandate of Crown corporations beyond oil and gas. So what is our plan? Well, the first thing that we do is we do a financial analysis. We do an unlevered analysis to, is this thing going to work out economically before we look at even technically. And when we're looking at Hinton, we're looking at the cost comparison of business as usual with natural gas versus geothermal. Right now, the delivered cost of natural gas there is about $12.30. In Hinton, if we get 75,000 gigajoules of baseload off-takers, we can get that down to about $12.27, so a 3-cent saving. Doesn't compare too much, but that's the initial investment. If we get this up to 150,000 gigajoules per year, that goes down to $9.81, so it's much better. If we get down to 225,000 gigajoules, it goes down to $8.91 or $7.91. These aren't pie in the sky numbers. These are numbers that we can actually tie into. Our first number of 75,000 was based on the 13 buildings that were owned by the municipality. I split things up into upstream, midstream, and downstream. Upstream, we're talking about the well and subsurface rights. This is where your greatest risk is, everywhere that we're talking about. And so we try to say, if we're going to split this up into 3 different investments, we have a different ROI with our upstream model. They're taking on a greater portion of the risk. That can almost become its own company. And we look at the upstream portion of it being research for geothermal formations, potential reservoir capacity. We're working with many different universities right now. I haven't worked with you yet. I will. But we've been working with Ryerson, Simon Fraser University, University of Alberta, and University of Calgary to look at this reservoir modeling. And also talking with SAGD operators, so steam-assisted gravity drainage. They have a tremendous knowledge base on reservoir modeling. The midstream is your district energy system. There's a proven technology that is, like I say, there's 20 of them just in Ontario, but all over the world. This is a mature technology. And then the downstream is within each business. So this is tying in the business units, tying in our customers. And so then I just have a little picture up here to say, what does this all look like tying all three of those up? So the far left side is your wells or your heat inputs into your district energy station, which is your middle part there. Right here we have 4 inputs. We say that we'd like to be heat agnostic, but it's heavily favored towards geothermal. And on the right side, this is tying into each one of your building load customers. So what we've done so far, we've met with our local regulators, local governments, and policy and academic institutions. We take a very collaborative approach where some people treat hydrocarbons as the enemy, treat the government as a insurmountable force to be reckoned with. We've actually had a very positive experience dealing with government, dealing with the regulators, Alberta Energy Regulator. We meet with them every 3-4 weeks, and it's been a very good learning experience for us, and a very good experience in general, as well as meeting, especially working with the hydrocarbon companies. We've surveyed the areas, both in all 3 of our locations that we're dealing with, and we've mapped out our potential opportunities, the value chain proposition, straight from taking heat from the ground to using your downstream model. So could be building heat, could be greenhouses, could be other industries. And we've engaged in local businesses. So what we need, next steps, is collaboration. Government collaboration, funding collaboration, academic collaboration, and then the financial collaboration as well. And that would be the end of mine. Perfect.
I want to kind of point out in this talk is that the geothermal industry in Ontario for heating and cooling buildings is changing very rapidly. And so I've called this industry on the move. I've been at this for 14 years, I think, and it's about time. It's been a real kind of a slow start and stop, but things are changing at a surprising speed now on a lot of different levels. So I'll point some of those out. I'd like to just point out some of our key alliances that Geosource works with. I am the Vice President of the Ontario Geothermal Association, the OGA that's written there, and I certainly encourage anyone here in the geothermal industry to be involved with that. We've got one conference in February, usually every year. I'll make sure I send out invites. A couple of the other ones that I really just want to point out here is McMaster University, talking about research collaboration. I was an academic at University of Windsor for 7 years in civil engineering, and kind of wanted to move a little quicker in terms of business, but I still enjoy the research. And geothermal has an awful lot of needs yet, even though there's plenty of people out there that suggest we know everything that we need to know about geo. I would beg to differ. Now that I've been in the industry long enough, there's a lot of things that we could use some help with. With McMaster, you'll see a little video a little later on there, but in their mechanical engineering group, they've built a small engineering building for 4th-year projects and so on. And under that building, we've put a thermal cell. And talking about, I was a little bit worried, so talking about from Manitoba there, the impacts of heating that ground up to 140 or 150 degrees Fahrenheit, what that might do to the foundations of that building. I didn't, anyways, it came up in conversation, but we didn't, anyway, so I just want to encourage that there's a meetup with McMaster at some point. They got a good group there. Even also doing some deep geothermal stuff too, doing research on that. They've got a great modeling group there. Okay, so just really briefly, I'm going to talk about what geothermal is. How does it work? I had one question in the audience, or earlier with someone who didn't really know what it was, so I figured I better put that up there. Why geo? Our business is construction of geothermal heat exchangers, so we do a lot of the drilling and so on. And then I talk a little bit about market, where the market's going, and if I got time, I'll look at this wind power thing, but we'll see. All right, so very briefly, what it is, and that technique of building ground loops underneath buildings is something that we've been doing for almost 10 years now and have it fairly well figured out how to do it and deliver. And one of the main reasons for doing it that way is, of course, footprint. We can get everything inside the building footprint up to about 30 stories underneath that building. And talk about local power, every building has its own power source from a heating cooling standpoint underneath its building. So it's all there. Okay. Why do we see geo happening? Well, one of the things is we see already to get carbon emissions down to where we want to be by 2050, electricity is going to be the power of the future. And it's not really a question of if, but it's a question of when. Okay, so when gas and oil are finite resources, although when they just started producing shale, that added a lot of life to gas, but we do know they're limited. And then, of course, our requirement to reduce greenhouse gas emissions is going to drive the use of electricity. Electricity on its own from a heating perspective is horribly expensive, so what we want to do is leverage that electricity use, and that's why we switched to geo, where we use heat pumps or chiller technology to extract heat from the ground in the wintertime, put it in the building, and reverse that in the summer and pull the heat out of the building and reject it to the ground and end up with some sort of a balance there. When we get into the high efficiency chiller technologies, we can get COPs or coefficients of performance of numbers of up to 6, which is normal residential heat pumps are sort of in range of 4 to 5 now. For every unit of electricity we put in, we extract, if we're in the heating mode, we would extract, with a COP of 6, we would extract 5 units of heat from the ground using 1 unit of electricity from the heat pump or chiller and put that inside the building. So it really does leverage the generation of power. And it's where we get our economics, certainly on the cooling side. Cooling is fantastic with geo because of low ambient temperature. And one of the things we are seeing, and we see examples of this, Ball State University, for example, has a very large district geo system where they are getting COPs up to what they call 14. Now, they're kind of double counting, but there's buildings in there that require cooling and other buildings that require heat, so they get this very high efficiency because they're simultaneously doing the heating and the cooling using the same compressor, so or chiller. So you get these. And then what we are seeing, the last point is the theoretical limit on heat pumps and chillers is quite a bit higher yet, particularly with the low lift of temperature that we need for doing space heating and cooling. But we are seeing this slow and steady creep up of these COP numbers, coefficient of performance, and we're the latest generation of variable speed residential heat pumps, for example, are seeing COPs upwards of 5. So I mean, there's a slow move up, and obviously improving the economics of the systems and so on. Okay, so this is what Geosource is. We're a drilling company that provides ground loops for mostly commercial buildings, condos, hospitals, and so on. And here's a picture of us in 2011, I believe, with a drill rig. These are dual rotary drill rigs that we drill casing, and then we have single rotaries that drill the rock typically. But we have a few rigs that we use to tackle different geologies. And the real key with the drilling, and one of my frustrations, and it happens, is we talk about research, but nobody's researching better drilling technology for geo. All it seems to fall back on the industry itself, but which is fine. It'd be great to have some work there, maybe in terms of robotics or AI, maybe even, because drilling is pretty boring. I heard talk about looking for boring energy. Well, drilling itself gets pretty tedious itself, especially when the rigs work. Then also, I've got one new rig now that can drill a 660-foot hole in shale in about 2 hours, and the guy never gets out of the cab. and it's like a robot, a remote control. He just sits there like this, and he's half the time he's kind of like got his head against the window because it's, anyways. Point being, it's the technology on the drilling side has advanced very far and very quickly in the last, I'd say, since we started. And what was a good day back when we started in 2004 was maybe a 200-foot hole in a day completed, and now we are pretty unhappy if we can't do 800 feet in a day. And we pushed holes. Used to be a 200-foot kind of the norm. We started pushing it. Now 600 is the norm for depth, and we're starting to do 800s and 900s. So just to get higher capacity out of the same footprint, those kind of things. Okay, so that's the one thing. And so in the foreground, first picture there, you see us drilling a condo in 2000 and underneath, like prior to the condo going up in 2011. The next picture you see in the middle or on the other side is that first condo is built up over top of the loop field now. This is in 2013. We're drilling, or 14. We're drilling under phase 2. And phase 2 is now done, and we just finished drilling phase 3. So this is in downtown Hamilton. And so you can see, kind of the progression of these things. Okay, next slide. So this is drilling a thermal cell. It's going under this building. It's called the Hatch Center in McMaster. It's obviously time sped up here just so you can see. But we're drilling down 85 feet. So it's very short. Holes are on 5-foot centers. There's 66 of them drilled in a kind of a cylinder shape, right? But it's still on a grid. And the intent of that is to do thermal storage, and they're doing district energy type planning where we do heat recovery on CHP, absorption chiller technologies, and so on. So there's a fairly large research effort going to happen with this cell, and there's a basement right beside it now with all sorts of equipment in there, and there's opportunity to put different types of equipment in there if you wanted to get involved in that. Looking at control strategies in terms of building controls, and modeling. Going to be simulating this thing to death, figuring out how it's working. Okay, so all right, so that's got some research opportunities. Now I just want to real quickly get into where is Ontario going with geothermal. 3 minutes. Okay. Of course, we all know that Ontario has a mandate to reduce its GHG emissions by, say, 37% by 2030 and 80% by 2050. The reality is, if we are going to achieve that, we need to completely replace all fossil fuels with something that doesn't produce GHGs. And there are not a lot of options out there. Geothermal's a great one. Air source heat pumps are out there. They're a little different, but Geo certainly is going to play a role. Right now, Ontario, of course, has a cap and trade program that is earning at presently around $2 billion a year. It's got a 1.5 billion right now, so far this year, and the intent for a lot of that green fund money or cap and trade funds is to promote low carbon technologies, and it appears that geothermal has made the cut. As involved as the OGA, Ontario Geothermal Association. I've been, again, working with regulators and policymakers and so on, working very, very hard to get geo recognized, and it will be, and I'm sure it's going to come big. Feds in the province have a lot of mandates to reduce all their buildings, and the universities and all those infrastructure. Ontario, for example, mandates to reduce their carbon emissions from all their assets. And one of the kind of real interesting thing is large utility players are entering the market. Enbridge is one that has publicly announced that it would be involved in geo. We are expecting them to start doing 1,000 homes next year, 2,000 homes, 4,000 homes. I mean, they're going to start rolling this out. That's the intention. And own the loops and rent the loops back to new homeowners. Okay, so that's big. And what we see right now is about a $10 million loop asset or loop construction economy right now in Ontario. I'm expecting that to be somewhere around 100 million a year within 5 years. So it's a very rapid growth. Not quite sure how we're going to meet it from the drilling sector, but I mean, we'll do our best. Okay, I'm out of time. Okay. Thank you.
Thanks everyone for the invitation to come and talk today. First of all, C-FER Technologies, we are a not-for-profit, independent research and technology organization in Alberta. We're double arm's length from the Alberta government, but owned by the government. We do all of our work with industry, trying to help them find the best available technologies and develop and evaluate those so they can implement them and make the wells safer and more efficient. Now, what we've been doing though is doing geothermal backwards for 30 years, is the short story. This is steam-assisted gravity drainage. It's been mentioned a couple times today already. It's the thing in Alberta that's released the oil sands, made it possible to produce the bitumen from the ground. There, they drilled 2 wells. The upper well, they inject the steam into. It melts, more or less melts the bitumen, drains down to the bottom well, and they produce that oil and water back to surface. Sounds kind of like enhanced geothermal systems. Now, some of the challenges they've had over the last 25 years or so developing SAGD is well integrity. You're operating at high temperatures, you're in a sour environment, you can even have stress corrosion cracking effects, all kinds of issues with the well, picking appropriate materials and configurations for those wells. Heat loss management. How do you get the steam down to the ground where you need it in the ground? It's fine having steam generation at surface, but how do you get it into the reservoir where it needs to be? Accessing the reservoir with horizontal wells, getting the wells exactly where you need to be. For this process to work properly, these wells have to be, they drill them down about 200 meters and they drill about half a kilometer, so 500 meters horizontally. And over that distance, they want those wells about 5 meters apart, but without very much variability, because you can imagine if the wells are too close together, the steam goes into one well at one point and doesn't get to the rest of the wellbore. So there's all kinds of issues they had to address on accessing that reservoir. On the reservoir management side, even distributing the steam along that long section of wellbore, considering the heterogeneities in the well, making sure the steam can go where it needs to go. You get a nice even flood of steam from one well to the other. Downhole pumping systems. These wells are operating at 250 degrees Celsius with multi-phase fluids, gases, non-condensable gases, steam, all sorts of things coming together. And coming up with a pumping system that can operate in that environment has been very challenging as well. And then scale management is another whole part, because you're injecting fluid, you're managing that water, all those different things. Now, this seems to line up really well with the list of challenges that John showed earlier that Forge is trying to address. The thing is, the SAGD guys have been working on this already. So I'm going to just talk a little bit about some of these technologies that have been developed and how we've been helping to evaluate those and how they might actually fit with geothermal. So first part is well integrity. Alberta Industry Recommended Practice 3 is actually a guideline for how to design thermal wells so that they last a long time, so they can survive in these environments. This IRP 3 was actually referenced in the deep drilling program that Maria talked about, that as part of the requirement for designing that well, they referenced the Alberta Recommended Practice. It's also part of the New Zealand standard for geothermal wells. So the world is starting to realize that Alberta's been doing this for quite some time now, and we've actually got some of these regulations and guidelines in place. The newest part is, it's a mouthful, but it's a thermal well casing connection evaluation protocol. So this actually grew out of the oil industry needing to design new kinds of casing to operate in these high temperature environments. SAGD operates at about 250 degrees Celsius, but there are cyclic steam operations that go up to 350 degrees Celsius. So getting a casing string to withstand that condition and not leak was a real challenge. We've been working on it for about 30 years, starting with work with Shell and Exxon. And in the last 10 years or so, the rest of the industry kind of got on board and said, well, we need to standardize this. So the TWCCEP, for short, not really that short, was developed by a group of manufacturers and operators to try to standardize the testing protocols for these connections. And most recently, that's now been adopted as an ISO standard. And our guys are actually helping chair those committees and develop that standard. The picture there shows one of our load frames where we're testing these connections, where we put the casing connections through a full life cycle, so in this case about 10 thermal cycles for the well to see how those connections perform at those different temperatures. And most recently, this standard has actually been used by a Japanese manufacturer trying to provide casing into an Indonesian operator for geothermal tested in Alberta. So it's kind of going in circles. Heat loss management, a lot of work going on alternative cements, both for insulative properties but also for zonal isolation, making sure that the new products are actually able to withstand these temperatures and loading conditions. Vacuum insulated tubing is starting to be used to limit the amount of heat that's lost to the formation. Again, when we're trying to heat the ground, we want the heat to go where we want it to. We don't want to heat up the overburden. In geothermal, you can get the heat to surface instead of losing it to the overburden. Insulated well bores. This is not in SAGD, but this is from the permafrost, from wells in Alaska, where the warm fluids coming up through the produced wells can actually melt the permafrost, causing subsidence and all kinds of problems with the well bore. So there's been a lot of work done on modeling those wells and designing them with different kinds of materials in the annulus between the tubing and the casing to try to minimize that heat loss. Again, it's not hard to make the jump to geothermal and making that process more effective. Reservoir access, so actually getting into the reservoir. Horizontal wells, they were more or less developed in Alberta to meet the SAGD drilling needs. Multilaterals, again, Halliburton was Sperry Sun first in Alberta. They pioneered a lot of these multi-side track systems where they can go in one wellbore at the top and branch out. So for geothermal, if you're having to go down 5 kilometers, can you go down 3 kilometers with one wellbore and then branch it out into the different wellbores? Is that going to be a savings in the well? And multi-zone hydraulic fracturing, again, not in oil sands, but again, developed by Packers Plus in Canada, in Alberta. This is the one picture here, the one on the left. That's the one that really kind of sold it for me to say we're actually doing geothermal backwards. So that's a multi-zone hydraulic fracture well with 100 fractures along the well. They're starting to call these zipper fractures now because they kind of look like a zipper. But what it actually looks like is a baseboard heater, right? Fin and tube heater, heat exchanger. They didn't know it, but that's what they're building with these things. They're building it to access the reservoir. That's exactly what we're trying to do in geothermal. So it's things like this, you start to see the parallels to what the geothermal industry needs and what the oil industry is already doing. Reservoir management, on another cool part here that's going on, downhole flow control devices. So here we have a horizontal well, and along that horizontal section, again, because of the heterogeneities in the reservoir, the steam can go in, will go in preferentially in the higher permeability locations. So what they're trying to do is control where that steam goes. So they use these devices called flow control devices. So there's injection flow control devices, so ICDs. There's also, or that's right, it's inflow control devices. There's also outflow control devices that control where the steam actually goes in the reservoir. Typically, these are devices that fit on the tubing that have some kind of a limited injection port on them, whether it's a labyrinth type pathway or a small diameter hole. The idea is that it only allows so much steam to go out in each of the locations, and then on the producer side, you have similar holes that only allow so much fluid to come in at those locations. So they're sort of a self-limiting device. The challenge was that because of the environment, high temperature, high pressure, multi-phase, the manufacturers weren't able to actually test these systems under normal operating conditions. So a group of companies got together, a bunch of operating companies got together, and paid us to build the fancy flow loop on the right-hand side there, where we can take one of these devices, put it through its paces at temperature, pressure, flow rates, multi-phase, and see how it behaves. We've actually now designed a second flow loop that takes those same devices and does erosion tests on them. Because as you can imagine, on the inflow side, you're getting material coming in with the oil and gas, or oil and water, that can change the properties of those flow paths. So we actually test the system first, or the device first, in the flow loop shown here, characterize it, see how it behaves. Then we take it out, we put it in our erosion loop, and we abuse it for about 3 months, simulating several years of production. Take it back out and put it back in the characterization loop to see how the characteristics have changed over time. So all this information is going into helping the operators develop better models for how to control these devices, or how to design and how to deploy these systems. So again, you can see where technologies like this would be really good in a multi-fracture EGS situation, perhaps, where you have some fractures that preferentially take all the fluid, that now you can decide where the fluid's going to go at what time. Downhole pumping systems, I think Thomas mentioned the need for high temperature pumping systems. These are electric submersible pumps used widely in the oil and gas industry, especially offshore. Again, challenge was for SAGD, they didn't know how they behaved with multi-phase, high temperature behavior. We built the flow loop on the left there, again with a consortium of operating companies. We're now testing pumps up to 250 degrees Celsius. Maximum flow rates, we haven't been able to test them, our loop doesn't quite go that high, but maximum flow rates for some of these pumping systems is 160 liters per second. So they're in the neighborhood of where the geothermal guys are looking to operate these things. One thing that's nice about, one other thing we've done with ESPs is the little diagram there shows that we have a sharing project for the last 17 years, collecting information worldwide on how these pumping systems are working, looking at failure modes, failure causes, and that information is available to all the operating companies, so they can actually look. So a guy from Shell can look at a guy's well from BP and see what he's doing, what kind of pumps he's running, what kind of run lives he's getting. So the whole industry can learn from each other about how these pumping systems are working. This would be an excellent thing to do for the geothermal industry, to bring that data together in one place so you can all learn from each other's mistakes or successes. More often the mistakes, though. We've heard about flow assurance as well today, some pictures of silica scale. Petrospec is an Alberta company. They offer, the picture there shows a coil tubing unit with various small diameter tubing and thermocouples in it. So these are instrumentation and chemical strings you can put into a wellbore. We were talking to an operating company out of California that was having all this trouble with their instrumentation strings and their chemical strings breaking and plugging up, and it was going to be a 2 or 3 week work over to pull everything out of the hole because they had to pull their whole pumping system and pull the instrumentation string and pull everything out, fix it all up, and put it all back down again. We introduced them to 2 companies, to Petrospec for one, who offer this coil tubing deployed system, so it's a bundle. They can run it into the hole in a matter of a few, like half an hour, and change things out if things are broken. We also introduced them to a company called Streamflow that makes thermal wellheads. And it has a dual wellhead, so you can have the pumping system on one side, and this coil tubing string can go in the side of it. So if your coil tubing string or your instrumentation breaks, you simply pull it out, put a new one back in without disturbing the pumping system. This company had a 10-year plan to fix this problem. Between Petrospec and Streamflow, they fixed it in 3 months. Just by technologies that already existed, that had already been developed for SAGD. So we've got this whole range of different technologies available to us. Again, none of them are actually ours. We've just been involved in testing them and understanding them and developing models and working with the operating companies to implement them. So we've heard it today, we've heard it many times already, demonstration project. To tie back the parallel to SAGD, this is the underground test facility. It was developed in Alberta in the early 90s, or late 80s, early 90s. All the modeling had been done on SAGD. Everybody thought it should work. Nobody wanted to take the dive to make it happen. The Alberta government stepped up through a program called AOSTRA, the Alberta Oil Sands Technology Research Authority. I think Roman was somewhat involved with that. It was somewhere around $100 million at the time. At the time, they couldn't actually drill the horizontal wells from the surface. You can see the little dotted lines there. They couldn't turn that corner because this is only 90 meters deep. So they actually had to mine underneath the oil sands and then drill up through into the oil sands to make these horizontal wells. Totally uneconomic. I think Farouk Ali, one of the big guys at the time, said the operating cost was $100,000 per barrel. The prices were high at that time, but they weren't quite that high. So totally uneconomic, but what it did was it demonstrated the technologies. It also pointed to a lot of the gaps, so the ability to drill horizontal wells from surface. the ability to build slotted liners for sand control, pumping systems, one thing after another. It identified all the challenges, but they were really well defined at that point. The service companies got behind it, the operating companies got behind it, and now it's a huge industry. So if we can do something like that, again, people have been talking about this. People have been talking about this all day here of can we make this demonstration project. The Forge project is doing the same sort of thing. We were going to try to see how we can fit in with that, but we still think there's probably an opportunity for Canada to do it on our own. So what we're talking about is enhanced geothermal systems. We need a better name for it. Getting the baseload capacity anywhere. If you can make EGS work, if you can simply drill deep enough, you can find heat wherever you need it, and bring it to the source, to the need for the power and heat. The World Bank has the Global Geothermal Development Program. I haven't heard that mentioned yet today. It's a great driver. They have identified geothermal as the power source to get the third world out of energy poverty. The challenge is that that program is focused entirely on conventional geothermal. So they're going in the African Rift Valley, they're going into some Southeast Asia, a little bit South America. So we've heard before that geothermal requires permeability, water, and heat. Now you got to toss a third world country on top of that requirement, and there's only so many places that it works. If you can make EGS work, now you can do it wherever you need that power. So that's the big picture of this. And finally, to tie it back to Canada, is the remote communities. We've heard a lot about that today, is the ability to do these small-scale power systems just about anywhere you need them, including the far north. So the vision is to get this to the energy mix, to diversify the oil field supply chain, because this is actually an export commodity for Alberta. It's not doing power. I hardly talked anything about making power actually in Alberta. It's all about taking the technology out everywhere else and helping everywhere else. And Iceland is already proving that. They're already showing that you can be an energy consultant and take your technology out. So that's the end of my story. Thanks very much.